So welcome back, students. We have discussed quite a lot of things in this lesson. We have seen what happens when a charge moves in a magnetic field. It experiences a force. And we have also figured out, since the moving charge is a magnet, what would be the strength of its magnetic field at a distance from the charge. There are two aspects that we have seen so far. That is like what happens to a moving charge when it is kept in an external magnetic field. That is one part. And then the second part is, because the moving charge itself acts as a magnet, what would be the magnetic field strength at a particular distance from the charge. Okay. And now we are going to go a little deeply, and then we are going to see the force experienced by moving charge or a current, or I should say that there is a wire which has current flowing through it, and what would be the force exerted on it by another wire which has current flowing through it. Okay, so that is what we are going to see now. So I am going to take two infinitely long, straight, thin wires. Okay, so there are two very long, thin wires. Okay. And they are separated by a distance r. The distance between them is r, right? Corresponding points on the wire. Okay. And let's suppose that I is the current flowing through the wire. This is I, or I say this is IA. Okay. IA is the current flowing through this wire. And let us suppose that the current IB is the current flowing through the second wire. Okay, I've chosen the directions to be parallel, but you don't have to take them to be parallel. You can make one of them in the opposite direction, and you can make them anti-parallel too, but it doesn't matter really. Okay, except the force direction would change. But for the time being, let's assume that both the currents are flowing in the same direction. Okay. So clearly, because the current is flowing through this wire, this is going to act as a magnet. And if you take this wire is kept in the magnetic field of this magnet. Okay. So this is going to experience a force, right? Okay, so there will be a force on this wire. And alternatively, I can treat this as a magnet, so this will have a magnetic field around itself, and I have this wire which has current flowing through it, and this wire will experience a force because of this magnetic field. Now I am going to calculate, or I am going to deduce what that force would be on each wire. Okay, that is the objective of this exercise now. Okay. Now, see, this is a long wire. And it can have, it's the length is kind of infinite, theoretically, if you think about it. So force will be acting on each and every part of the wire. So I'm going to take a specific section of the wire. Okay, maybe this section. Let's see. Okay, this section, that is length L. L is the length of the wire, and I have the same length here. Okay. The same length here, same length. So I can figure out what the force would be on this particular length of the wire. And again, so other pieces of the wire will have the same. They'll also experience a force, but my focus is right now on this particular segment of the wire. Okay, what would be the force on it? Well, what would be the force on this? Let's say I'm trying to figure out the force acting on A. This is conductor A, this is conductor B, right? So force acting on A will be equal to current in A, IA, and then length. So okay, I'll take this direction. Okay, so L. Okay, cross IL cross B, which is B due to the external magnetic field. So what is the external magnetic field in this case? It's a magnetic field due to this wire. So this wire should produce a magnetic field here, okay, and that is the magnetic field value I will take. Okay. So IA is the current flowing through this wire, L is the length of that wire, but then B is the B due to this wire, this magnet. Okay. So B due to B. Okay. So this is a force experienced by this segment. Okay. Well, now I need to find B due to this wire, right? Okay. So think about it. IB is flowing in this direction. So you see, I can expect the magnetic field to be around it. Okay. A curve. You curl your fingers around this conductor. That's the direction of the field there. So clearly, if you think about it, here you see the field will be coming out of the board. Okay, the field will be coming out of the board at this point because of the circular nature of the field. So it will be coming out of the board. So B direction would be this. B would be coming out due to this. Okay. Here on this side, B due to this would be going in. Okay, because you see it's like that. But here it will be coming out. So BB is coming out all right. But what's the magnitude of the BB? Well, I can use the Ampere circuit law to figure that out. Or like if you know from your reference and previous classes, you can also use it value. But I'm going to use the Ampere circuit law to figure that out. First, I'm going to take, okay, instead of this, I'm going to take it like this, right? Okay, I'm going to just tilt it like this. Suppose this current is flowing through it. So I'm going to find B here, right? B is, I need to find B here. So what should I do? I need to make a circular area. I need to imagine an open surface, a circular open surface. Okay? So now B would be, the magnitude of B would be equal at every point, it would be the same at every point on the circle. The direction will be different, but that is okay. But magnitude would be the same. Okay, so what do we know? If we do a B dot dl around that circle, a closed loop integral B dot dl, and that must be equal to mu naught times the current piercing through the circle, right? So that's the idea. That's exactly what I'm going to use. So, I mean, instead of saying it like this, I am saying it like this. Okay, like seeing it like this. Okay, I'm looking at it from this perspective. So, how am I seeing it? I am taking this. Current is flowing into the board. That is how I see it. That's my IB. So, magnetic field will be around it, right? So, magnetic field will be around it. So, what would be the field value here? So, that would be, I'll take this this surface area. So, I'll do B dot dl, right? And this let's say the distance is r. If I want to find B at that position, what should I do? I need to take closed loop integral of this open surface B dot dl. In this case, BB, right? This distance BB dot dl must be equal to mu naught times IB. You see, what's the current piercing through that? That's IB. IB now. Okay, so B is constant because it's going to be the same at every point on the circle because symmetry argument. So B can be taken out, and I'm going to have integral dl, and cos theta would be 1. So because B will be in the same direction as dl, so the angle between dl and B will be 0, so cos 0 will be 1, so I can just ignore that. So this is what I get, mu naught IB. But if you keep adding dl throughout the circumference of the circle, then I am going to have the length of the circumference. Okay, so that gives me BB is equal to, this is 2 pi r, that is equal to mu naught IB. can see that as you go, okay, I'll say BB is equal to mu naught IB by 2 by R. You can see that as you go away from the wire, B will keep reducing. You see, as you go away from the wire, R will be greater and greater. So B will become smaller and smaller as you go away from the wire. Okay, so that is there actually. Okay, now I know the value of B. Okay, so I know the magnitude of BB at this point. So BB is mu naught into IB by 2 pi R is the magnitude there, and it will have a direction. This will be coming out of the board at this point. Okay, and it will be the same at every point, right? Because of symmetry, B will be the same throughout the wire. So here, 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 everywhere it will be the same. It's long, infinitely long wire. So like it said, it will have the same value on both sides. Okay, let's see. What I'm going to do is this. So what is my force? Force acting on A is going to be equal to IA. Alright, now L is in this direction, B is in this direction. So what is this? This is going to be IA, L, B, B, and what is the direction? What is the angle between them? L is like this and B is coming out. So the angle is 90 degrees. You can see that. So 90 degrees. So sine theta, sine 90, and the direction is going to be which direction? So it is IL, this direction, B is in this direction. So IL cross B, you see the thumb is pointing in this direction. So this will experience a force in this direction, FA. So this will get attracted towards that wire, towards wire B. Okay. So direction is this. I'll say, I'll take this as the x direction. Okay. So I'll just say that this is I. Okay. So that is that. And if I just put these values there, then this is going to be IA, and then L, so mu naught ID by 2 pi R in the I direction. So what I'm going to get now? So mu naught L IA IB by 2 pi R in the I direction. So that's a force experienced by A. Okay. So this is going to be the force experienced by L length of the wire. Okay, if the L is 10 centimeters, then you will have one force. If the L is 1 meter, then the force is going to be more, right? So if it is 10 meter wire, then the force is going to be even more. Okay, so it depends on the length of the wire, the force experienced by this. So I can do one more adjustment to this manipulation of this equation. I can bring this with L down. F A by L. That is force experienced by unit length of the wire. The force experienced by the unit length of the wire can be given by mu naught IA IB by 2 pi R this direction. So this will be in newtons, and this will be in Newton per meter. Okay, so that is the force experienced by this wire per unit length. Okay, let's see what happens to this wire because of this. Clearly, as far as this wire is concerned, this will act as a magnet, and this current carrying wire is kept in an external magnetic field of this wire. So this will also experience a force, right? So let us see how that would be. Okay. So I'll try to calculate FB. What is FB? Force experienced by this wire for length L. Say now current is IB, current through this wire, then same length L, this direction, cross B due to A, B due to this wire. That's going to act as a magnet for it, right? Okay, so this again will give you, by using the same logic, I'm going to get IB and then L, then B into A. Okay. And sine theta would be, sine 90 will be 1. See, let's see like what would be the direction of this field. Okay. First of all, IA is going this way, so you see it's like this. Okay. The B will be going into the board here. So BEA is actually BEA here going in to the board. So that's BE going into the board there. Okay. So now, what would be the force now? Let's see. BA is now into the board. IB or IBL is upwards. So IBL cross cross BA will give you this direction. So the force acting on this will be opposite direction, FB, in the opposite direction. Okay, so that is, if I take that to be I, this direction to be I, this direction is actually minus I. So the direction is going to be minus I. Okay. So sine, actually the angle between I and B is 90 degrees, so sine 90 will become 1, so I'll get IB, L, BA. Okay. But then the direction is going to be in this direction, opposite, okay, to FA. Okay. So you see, now this is getting attracted to this one. You can see that this wire is getting attracted to that wire, and that wire is getting attracted to this wire. So the wires will come closer now. So I want you to understand that. Anyway, so what would BA be? Using the same logic that we have used here, BA would be, well, again, imagine a circle here, at the same distance r, right? Circle here. So then mu naught IA will be equal to BA dot DL. Okay, so that would give you again mu naught IEA, it's going to be 2 pi r. So BB is mu naught IB by 2 pi r. But BA, the field due to this current is going to be mu naught IA by 2 pi r. Okay, so you get this and use this expression here. So FB is equal to IB L mu naught IA by 2 pi r minus I. Okay, so that gives you FB is equal to minus mu naught L IA IB by 2 pi r. Notice here, the magnitude is the same, but the direction is opposite. See, Newton's third law is obeyed. Every action will have an equal and opposite reaction. So if this is pulling it, if this wire is pulling this wire with certain force FA, this wire will be pulling this wire with an equal amount of force in the opposite direction. Okay? If this pulls it, and that will also pull this one. Okay, so you get this. And again, coming back to this, I can do FB by L, that is force acting on it per unit length, going to be equal to minus mu naught Ia Ib by 2 pi r, the I direction. Okay. So again, this will be in Newton and this will be in Newton per meter. There is a force experienced by this conductor per unit length. Simply mu naught into Ia Ib by 2 pi r. See, this arrangement can be used to define Ampere theoretically. What is Ampere? Ampere is a unit of current. Okay. So, how to define Ampere using this? Well, suppose I send 1 ampere current here and then 1 ampere current there. Then what do you think would be the value of this? And suppose I'm also separating them at a distance of 1 meter. So I take an infinitely long thin wire, or actually 2 of them, and send 1 ampere current in both of them and separate them at a distance of 1 meter. What do you think is going to be the force experienced by it? Okay. So, can we do it? Okay, let's see. In this case, what is going to be FB or FA or F by L? What's going to be the force per unit length? That's going to be equal to mu naught, this is 1 ampere and that is also 1 ampere, and then 2 pi, and then they are separated by a distance of 1 meter. Okay. So that gives you mu naught by 2 pi. So, but what is mu naught? So F by L, mu naught. So 4 pi to 10 power minus 7 by 2 pi. So this will go, so that gives you 2 into 10 power minus 7 Newton per meter. Okay. So what happens now is, when you have a very long, thin, straight wire, in fact, when you have 2 very long, thin, straight wires, and when 1 ampere current is flowing through each of them, and if these wires are separated by a distance of 1 meter, then they will experience, each of those wires will experience a force 2 into 10 power minus 7 Newton per meter. For unit length, they are going to experience 2 into 10 power minus 7 Newton force. Okay? So that is how you define Ampere also. So how do you define Ampere? Ampere is the amount of current that flows through 2 very long, thin, straight wires which are separated by a distance of 1 meter and causes a force of 2 into 10 power minus 7 Newton per unit length of each of those wires. Let me repeat. Ampere is the amount of current that you send through 2 very long, thin, straight wires which are separated by 1 meter and causes a force of 2 into 10 power minus 7 Newton per unit length of each of those wires. Okay? So that is the definition of Ampere. This again, if you think about it, if I change the direction, I'm sending Ia and Ib in the same direction, these wires, and then they attract. When currents flow in the same direction in the wires, then the wires get attracted. Suppose the currents flow in the opposite direction in the wires. So one is this way and the other one is this way. Then what will happen is you can do it for yourself and find out that they will repel each other. So opposite currents will repel each other and same currents will attract each other. Okay? slightly different idea, right, from electrostatics. Electrostatics, you thought same charges will repel each other, and opposite charges will attract each other. But here, currents flowing in opposite directions will repel each other, and currents flowing in the same direction will attract each other. Okay? You can do it using your the vector cross product here, or using your right hand. Let's say, suppose this current, I am changing the value of this current. Suppose it's going this way. It's going this way, right? So what will happen now? Here you notice it is going this way, current is going this way, it's going this way. Then you notice that the field will be around it like this, right? Because this is going to show the direction of the flow of the current, and then the field will be like this. So now BA here will be out, right? It will be out now. So BA will be in this direction. IB is up. B is like BA is the same. So IB cross BA is this way. Notice that FB will now act in the opposite direction. So it will push the wire that way. Okay. So this wire will go that way. But what will happen here? Well, because the current is flowing in the same direction, BB is still out. BB is still out, but then you see you change the direction of IA, right? So IA is down, BB is still out. So IA cross BB is out this way. So this wire will also go that way. So that wire will go that way, and this wire will go this way. There will be a repulsion. So if you change the direction of this current or that current, in any one current, if the currents flow in opposite directions, then the wires will repel each other. If the currents flow in the same direction, then the wires will attract each other. Okay? So that is what is happening here. And this is how we define the ampere also. So ampere is the amount of current that is flowing in each of the two long, straight, thin wires, okay, which are separated by 1 meter, that cause a force of 2 to the 10 power minus 7 Newton per unit length of each of those wires. So that is how you define ampere. Hope this is clear to you. Okay, let's do an example problem now. Example 4.10. The horizontal component of the Earth's magnetic field at a certain place is 3 into 10 power minus 5 Tesla. And the direction of the field is from the geographic south to the geographic north. A very long straight conductor is carrying a current of 1 ampere. What is the force per unit length on it when it is placed on a horizontal table and the direction of the current is east to west and south to north? Okay. So what they've said is this. So the external field is the Earth magnetic field. Okay. So as I stand here, this is north and this is south for me. Okay. So this is north and this is south. So if you see the Earth magnetic field, it will be going from south to north. Okay, it's slightly different from what you see in your magnet. If you take a bar magnet, you will see the lines going from north to south. But in the case of Earth magnet, what we call as a north pole is not exactly magnetic north pole, it's actually magnetic south pole. But you started calling that as north pole, so that name has got stuck to it. Okay. So in the case of Earth magnetic field, what you call is not actually not north, and what you call as south is actually not south. So your what you call as north is actually south, and what you call as south is actually north. Okay? So the magnetic lines are from what you call as south to what you call as north. Okay? So it will be like this. Okay, so we'll talk about it a little in a little more in detail later, but just understand that as far as the Earth's magnetic field is concerned, the magnetic lines are from south to north, what you call as south to what you call as north. So that's the only thing that you need to keep in mind. Okay, so now let's see. So it's like this. So here, if I take my case, this is south, this is north. So the field is this way. Magnetic field is this way. So there is a horizontal component of it. Actually, Earth magnetic field is not very straight. It can be upwards or downwards at a particular point. At this point, if I take, it can be like this, or it can be like this. Okay? All that we'll study a little later. But then we'll worry only about the horizontal component now. The horizontal component is, because if the field is like this, I'm going to take only the horizontal component. I'm going to ignore the vertical component. Okay, I'll take this horizontal component. So let us suppose the magnetic field is like this. Earth magnetic field is like this. Now the point here is that I'm going to have a conductor carrying a current of how much? Current of 1 ampere. Okay, so long conductor, it's very long, maybe it starts from here and then maybe ends there. It's a very long conductor. I'm keeping it on a table in the east-west direction. East to west. Now the current is flowing from east to west. Which is east for me, this is east for me. East to west. So the current is moving in this direction. And what is the field direction? Magnetic field, the Earth's magnetic field direction. This is the field direction. So what would be a force experienced by the conductor? Well, the force experienced by the conductor, 4.10, force is equal to I L cross B. Right? Okay. Okay. So what is the current through this? Current through that is 1 ampere. So this 1 ampere is the current which is flowing through it. And then L is not, depends on the length, right? Maybe 10 meters, it may be 1 meter, it may be, the 20 meters, doesn't matter, right? Into, what does this be? L into B. B is 3 into 10 power, 3 into 10 power minus 5. And sine theta, what's the angle between them? The horizontal component is this way, and then it is east to west. So the angle is actually 90 degrees. So sine theta is equal to sine 90, it is 1. So what would be the direction of it? What is the direction of it? B is this way, current is this way. So IL cross B down. IL cross B down. So this will go down. The force will be acting down. Okay? So that is F. And what do they want now? They want the force per unit length. So bring L down. So F by L is equal to 1 into 3 to 10 power minus 5. Sin 90 is 1. So that's going to be 3 into 10 power minus 5 Newton per meter in the downward direction. So for every meter, there will be a force of 3 into 10 power minus 5 Newton acting in the downward direction. Okay, so that is a force acting on that long conductor carrying 1 ampere current being kept in the Earth's magnetic field, which has a horizontal component of 3 into 10 power minus 5 Tesla. Okay, so that is part 1. Then second part, what if we keep the conductor south to north? Well, south to north. Second part is south to north. So this is the first part. Second part is south to north. So instead of keeping the conductor like this, I'm going to keep the conductor like this. So 1 ampere current is going to flow through the same conductor. But then what happens here? B is the same direction as L. So B cross L or L cross B will give me a sine 0 there. Sine 0 will become 0. So the second case, if I keep the conductor in this direction, the conductor will not experience any force at all. Even though you have a B, even though you have an I, this conductor will not experience a force because IL, that vector, is in the same direction as the B vector. So they won't experience a force at all. The conductor will not experience a force. The force acting on this is equal to I L B sine theta. Okay. And here it's going to be sine theta is going to be sine 0, so it doesn't matter, it's going to be 0. So no force will be acting on that conductor. Even though current is flowing in that conductor, even though you have an external magnetic field, this will not experience a force at all. And if we keep it in the east to west direction, yes, it will experience a force. The current is flowing in this direction, it will experience a force down. Suppose the current is flowing in this direction, then it will experience a force up. Okay? But it will not experience a force, any force at all, if I keep it in the south to north direction or north to south direction. In that case, you will either have sine 0 or sine 180. In both cases, the magnitude of the force will become 0 because sine 0 is 0 and sine 180 is also 0. So no force will be experienced if I keep the conductor in this direction. Okay? Hope this is clear to you. So the next topic that we are going to cover is torque for magnetic dipole. Okay, so this is going to be torque. So what is a magnetic dipole? It is, as we saw, it is simply a loop of current, right? Like if you have a current carrying loop, then that can be considered as a magnetic dipole because you will, for the first time I told you that you would have a north and clear south poles when you have a current carrying loop. Okay? Even though we talked about a circular loop in that case, even any other loop would also behave the same way. The loop that we are considering now is a rectangular loop. Okay? So this is the conductor which is connected to a battery. So this will send a current through this, right? So this is a current which will flow through that loop. So this could be A, and that's B, C, and then this is D. And this loop is kept in an external magnetic field. Maybe it's like a horseshoe magnet, where you have a north pole here and then the south pole there, and then the green lines signify the field lines. Okay, so you are keeping that loop there. So you have a current carrying loop, so that will experience a torque. That's the whole idea. And that loop is also a dipole, a magnetic dipole. Okay. Let's see what happens here. So this loop is connected to this battery through a slip ring arrangement. Okay. So that the current, the direction of the current will be the same, even if it rotates and then comes this comes here, it will still be, the current direction will be the same, so you can maintain the torque. That's the idea. But let's maybe a little bit jumping ahead of it. Let's see what happens here first. I have A, B, C, D. There are 4 parts: A, B, B, C, C, D, and D, A. Okay? Because let's suppose it is this distance is very small, negligible distance. Okay, that separation is small. So it is like this segment, this segment, this segment, and also this segment. There are 4 segments to that. And let's see what happens now. See, all these segments will or potentially can experience a force. Why? Because they are current carrying conductors, they are kept inside a magnetic field. And let us see what happens in this case. So it's like this. You have a loop like this. So this is A, B, C, and D. A loop like that. And then this kept in a magnetic field like this. And current is now flowing in this direction. So let's see what is the force experienced by this part. Okay, the force experienced by AB. ILB, right? So I is the current flowing through it. L is its length. So I'll call that length to be B. I'll say this length is actually B. This is B is the length. And I will call this length to be A. Okay. So this will experience a force of I, this small b, and B is the magnetic field strength, capital B. So B is the magnetic field strength and this is B. I is the current flowing through it. And notice sin theta would be 90 degrees, right? Sin theta will be 1. Because theta will be 90 degrees. B is in this direction and IL is in this direction, so 90 degrees. So IBB is a force experienced by this current, this segment. And which direction would that be? IL cross B inwards. Okay? So the force will be into it. Okay? So this is the direction of the force. This segment will experience a force in this direction. It will be pushed in this direction. Okay. Now, what will happen to this part? BC part. BC and like this IL and B are in the same direction, notice. So it won't experience any force because sin theta is 0. So this force experienced by BC will be 0. Okay? And what about force experienced by CD? Well, same current I is flowing and this B, that length is B, so that is in this direction and magnetic field is in this direction, so IL cross B, okay, so IL cross B in this direction. Okay? So this part will experience a force in this direction. So that is again L is actually B, small b, and then D, and it's in this direction. So this part will experience a force in this direction, and this part will experience a force in that direction. Okay, so there will be a rotation possible. Okay. This will try to come this way, and this will try to go that way. So rotation is possible. And before we conclude, we will do this also. So the force due to the current and then the magnetic field on this part, which is dA. Again, current will be in this direction, B is in that direction, so sin theta will be 0 because theta is 180 degrees, right? So ILB sin theta will be 0, so there will be no force acting on this. So no force on this, no force on this, but a force acting on this and a force acting on this. But then the force acting on this is in that direction and the force acting on this is in this direction, so there will be a rotation possible. It will rotate about a central axis. Okay, so that is how this rotation is going to take place. Okay, so it will rotate this way. So it's like this. Rotate this way. Okay, hopefully this makes sense to you. And once there is rotation, then clearly I can talk about the torque acting on it. Right? Okay, so the force is here, and this is the axis of rotation. So I can find torque about the axis of rotation. So force, and then this is the distance. So R cross F will give me, right, the torque, right? So it's like let me stand in the center of the axis of rotation, and this is my R. Then force is in the direction. So R cross F is down, right? So the torque acting on this. So torque acting on AB is equal to R. What is R? R cross F. That is actually A by 2. And then F is I, B, B. And then sin theta is 90 degrees in this case, right? Because force is acting this way and R is this way. So R cross F this way. So 90 degrees there. So clearly that is going to give me sin theta 1. So that is the force, that is the torque, and that will be in the downward direction. And the torque will be, for this will be 0, and this will also be 0. So I don't have to worry about this, but then I can find torque for this, right? So now the torque on the CD. Again R cross F. What is R this one? R is the very center. This one will be this R. Okay, R is in this direction. F is in this direction, right? So R cross F. R, F is in the R cross F. So again down. So A by 2 I B B, all right. And sin theta is 90 degree, and we down. So what's the total torque? The total torque is simply torque AB plus torque CD, and both of them are acting in the same direction. So it will be a simple vector, a simple addition. No. So that would give me I, A, B, B. And then what is this AB? This AB is the area of the loop. So I'll say again now, right? So the torque is actually I, A, B down. So this A is the area of this. Okay, so that is what happens when the loop is like this. But then once the loop starts moving, the node is here, then the force is acting in this direction, but then notice that R is getting reduced. Okay? R will be getting reduced because it will go this way. So the torque will change as it starts moving. And this is where it will have the maximum torque because force is like this and R is also like this. But then once it starts moving this way, look, R gets reduced now. That's going to be A by 2 sin theta kind of a thing. Okay, and when it is like this, when the loop turns and then becomes like that, there is no torque acting. Why? Because there is force in this direction, there is also force in this direction, and from the center, there is no perpendicular distance, you can notice. Then it will be a 0. So because the forces will be acting in the opposite direction, they won't rotate this stuff. Okay, so here it will start rotating, but then the torque will reduce, and then it becomes 0 at this point because even though there are forces, they are acting in the opposite direction, in the same line, so it will become 0. So the torque from the maximum value like this will reduce as you go down. Okay. So at any particular point, you can see that if this is that, if it is like this, okay, if this is B direction, okay, if force is in this direction, force kind of like if in this direction, you notice that this is A by 2 and this is A by 2, and then this angle, the torque would be actually, this is theta, then A by 2 sin theta is what you would have. Okay, that's the thing. Okay, so what happens now is that this torque actually becomes something like this. Okay, this torque is equal to I A cross B. Okay, so in that case, and say I'm going to use A as a vector. So A as a vector. What is A a vector? Is area a vector? No, because but I'm going to take it as a vector. But the moment you take area as a vector, see, then I'll take the normal as direction, right? But now I have two things. I'm going to take this normal or this normal. Is it this direction or this direction? So I would say that the direction I'm going to take is going to be chosen like this. I'm going to curl my fingers around the direction of the current. Let's suppose the current is flowing like this. I'll fold the finger like this. Then I'll get M. I'll get this direction. Okay, so that would be the direction of A. Suppose the current is flowing like this. Then I'll curl my fingers like that, and this will be the direction of A. Okay, why? Because only then I can get the direction right. Okay, I'm going to have this quantity first. I'm going to call that quantity as M, the magnetic moment. Okay, I'm going to call that quantity as M, magnetic moment. And then I'm going to call it as M cross B. My tool now is going to be M cross B. If this is what I'm going to have, then what should be the direction of M? So M cross B must give me tau. So as I said, current is flowing in this direction, B is in this direction, and then I said tau was down, right? So if M is in this direction, M cross B will give me downward direction. So how can I choose that then? If current is flowing this way, then this would be, if I curve my fingers around the current direction in the loop, then the thumb will give me the direction of M. So now, when current is flowing like this, M is in this direction, B is in the direction, so M cross B will give me a direction, the direction of torque. So this is how I do this. Okay, so M, in this case, M is called as magnetic dipole moment. Okay, and the magnitude of that is IA. If there is only one loop, if there are multiple loops, if there are n loops, then my M will become n times that IA. Or I'll rearrange it and I'll say NAI. So the magnetic dipole moment M is NAI, NAI. It's very easy for you to remember it that way. So I have a conductor which is made into a coil or something, okay, a loop. So let's suppose there are n turns in that coil, and suppose I know the area of that coil, and so suppose I is the current flowing through that coil. So the magnetic dipole moment of this is given by this expression, M is equal to NAI. So it's very important. In this case, it is M is equal to IA because I'm considering only one turn. N in this case is 1, so M is IA. But the magnitude of M is calculated this way. M is equal to NAI, NAI. Very easy for you to remember. A is the area of the loop. Okay, the greater the area, then the greater the magnetic dipole moment will be. Or the greater the number of turns, the greater magnetic dipole moment will be. Or if I send more current through this loop, then also the magnetic moment will be higher. Okay, so this is tau is equal to m cross b. Why am I coming up with this kind of an expression? Because I am trying to make it analogous to what is happening in the electric dipole. Okay, in the case of electric dipole, how did you find the torque? The torque in the case of electric dipole, which was kept in an external electric field, was P cross E. Remember? You see, this is the field, external field, and this was the dipole, electric dipole moment. Likewise, when you keep a loop which is a magnetic dipole inside an external magnetic field, then the torque is given by M cross B, where B is the field, just like E, and then M is the magnetic dipole moment, just like P. But the difference is P is simply Q into L, the distance between the electric charges. But here the M is actually NAI. Okay. But the moment I define my magnetic dipole moment as this, then you see that this equation and this equation becomes analogous. You have the magnetic dipole, you have the dipole moment, and then you have the field. So dipole moment cross the field will give you the torque, whether it is electric or magnetic. In the case of electric charges, the electric dipole, again the torque experienced by the electric dipole is the electric dipole moment P cross the external electric field E. Okay? And in the case of magnetic dipole, the torque experienced by magnetic dipole is the magnetic dipole moment M cross the external magnetic field B. See, there is an analogous situation here. This equation is analogous to this. So for that purpose only, we are defining the magnetic dipole moment like this. Okay. I hope this is clear to you.